Good afternoon. So it's my challenge for you to keep you all awake, I guess, actually. So I'll do my best. Um, the work of what I'm presenting today is a collective of various scientists within Texas A&M University System, but also our partners, especially IFPRI and IMI. You already heard the three presentations this morning from IFPRI and IMI about the data collections and the field work and the analysis that were conducted actually. So all those information fed into our modeling activities in terms of analyzing not only at the site scale or a farm scale, but also at the regional and national scale. So I'll go through this very quickly. There are lots of slides here. So at the beginning of this project, Conceptual Station, one of the things that we wanted to ask is, we are going to have limited number of sites where we can do analysis. We have a limited number of places where we can conduct surveys. And so how are we going to be able to expand this analysis beyond those study areas, for example, actually, especially for scaling up activities and so on and so forth. Some of the key questions came out of that exercise were how much land is available, actually. And do we have enough water for them, actually? How many farmers may be benefited from this process? Is it going to be sustainable? This is becoming a very key questions over the period of this entire project, actually. And then, of course, what are some of the constraints and opportunities, actually? So we have, because whatever we studied on this small set of farm systems on the ground may give us only a limited opportunity to explore what's going on there, actually. But there are so many other questions or other constraints that we may or may not be able to evaluate by just the field work. So these are all some of the things that gave us the food for thought in terms of going through how do you come up with the optimal interventions, or what are the what is it going to make a difference in terms of income or health or lives of the people, and so on and so forth. So we used a suite of models. In this case, I'm just showing the three. In fact, I should add one more model that IFPRI has come up with, agent-based modeling in our suite of models. So the three models were developed at Texas A&M in cooperation with the USDA, ARS, and NRCS, and others. These are all well-known models. The SWOT is a model that's meant for environmental and water resource analysis at regional and national scale. APEX is a farm scale analysis, and then of course FarmSim is an economic analysis tool. All these tools been in existence for well over 30 years actually. And these are all very well proven models that have been used over and over again for various national analysis in US. And now we are applying this to beyond US also, actually. And beyond US is not a trivial task. It does poses a lot of challenges, but it's been successfully implemented in more than 90 different countries, actually. So they have long track record of using these tools for natural resource assessments. So where did we use this model for, actually? At the first year of our project, where we didn't have enough data from the field, because field interventions has just started and data collection has been started. So we used this as for ex-ante analysis. Then when we did get the data from the field, from the year 2 to 5, we are using it as an ex post. Ex post meaning we collect the data from field and verify whether the model is able to reproduce what we collected from the field, actually, including looking at the various variabilities within the field in terms of either farm size or cropping systems or irrigation technologies, irrigation water resources, and things of that nature. Then, of course, we also looked at gaps and constraints. That's not what was not observed in the field. How can we go about using models to evaluate some of them, and upscale. So once you understand this, we are able to upscale to the regional and national scale. And later I'll come and talk about capacity building. So I'm just presenting a very not even a 1% of what all the analysis that went on. We have extensive report from each individual site to regional to a national level reports for each of this country. So we highly recommend you to take a look at our website as well as the USB drive that has been distributed here that may have a lot more detail about all our work actually. So I'm just going to present you a few of the studies, especially this one is in Ethiopia. And the average rainfall in this watershed is about 1,400 millimeter. Of that, the groundwater recharge is about 280 millimeter, and surface runoff is about 520 millimeter. The remaining is mostly ET during growing season, actually, during wet season. Okay? So if you have to take this water that's going to be available and use it for a dry season crop, let's say, for example, tomato. Okay? We evaluated almost literally about 12 to 15 different horticulture crop and pulses and fodder and things of that nature. So the amount of water that's required for this watershed will be about 1.5 million meter cube of water, actually. So you can already see we have well exceeding that amount, actually. But of course, this is a direct runoff. Unless you store them, you can't use them during the dry season. So you have to have some kind of a storage facility or like a water harvesting structures. So we have studied that also to an extent, but I'm not presenting that here. But mostly we are targeting the groundwater resources for this application or for this irrigation source, actually. So we need only less than about 40% of the water that's stored in the groundwater could be easily used to produce the vegetable crop here. In this case, is tomato. So that means we have plenty of water, actually. So water is not a scarcity, especially for this particular watershed. Okay? So here is an example of land suitability. Just because there is water, that means you cannot throw irrigation everywhere, actually. So there are limitations of where you can apply irrigation. So that's another outcome or output that comes from this analysis, from the IDS analysis, is where you can, what is the suitability of applying the irrigation systems, actually. The red being low, and I know you won't be able to read that very clearly, actually, and blue being the highest probability, actually. So obviously in the head watershed, you may have limitations because of the high slopes, steeper slopes, soil may not be conducive, and so on and so forth. As you go downstream, you may have a better option to use irrigation. We did simulate both the wet and dry season. The model is a continuous time step model. That means it has to simulate the entire cropping system. We can't just isolatedly look at only dry or only wet crops, actually. So we have to look at the cropping system throughout the year. So I mean, the wet season, it's maize, teff, or finger millet. And in the dry season, it could be either vegetables or pulses or any of the crops that normally grown during the dry season. Oh, sorry. I don't know why it went so fast. Okay, so the model is also capable of looking at the environmental impact. That could be sediment, that could be low flows or high flows and things of that nature. So what we are showing you here is based on the direct runoff between the baseline and the scenario analysis, you're not seeing that much different, the blue and red line. They're almost very similar. That means we are not affecting significantly the flow in the river in using the water for irrigation. Even though we are pumping the water from the groundwater, that means the water is coming out, actually, but the amount of water that's going to recharge is not affecting significantly your stream flow. That also goes into, we looked at into sediment analysis and other output also from the model to make sure environmentally we are able to produce these in a sustainable manner. Okay, so here it shows spatially where the water is available or water is coming as a surface runoff, as well as groundwater recharge, how much water is going to the ground. So I'm showing you this at the local site level where we had the detailed data, that's collection effort that went on with me and our partners and the local partners such as the universities like Bagadar University and things like that. But this can be scaled at regional and national scale. But all our verifications and validations were done at that local scale before we did anything at the national and regional scale. We also looked at things like water functions, meaning how much water is required actually, how much water is applied, that's your x-axis, and how much is the yield potential here actually. So as you can see, if you had only 100 millimeter water to irrigate, whatever the constraint may be actually, maybe it's a technology constraint or it could be equipment constraint or whatever that you have that. If you had only that, you are losing a yield. Your yield is somewhere around 20 to 22 tons actually, whereas the maximum potential may be around 40 to 45 tons actually. Okay, so this shows you, this curve basically shows you the yield potential against your water application rate. Just because you keep on applying water, that doesn't mean the crop is keep on going to grow either, actually. So that's where you're seeing somewhere around 400 millimeter of irrigation is all you require, actually. You don't need any more, actually, because your yield is flattening at that point. But keep in mind, just because the dry season, that means there is no rain at all. No, there are some rain also during the dry season. So this we are looking at and running the model over a 30 to 40-year time period, look at the various climate resilient issues, actually, in terms of dry season, dry years, wet years, and so on and so forth, actually. Okay. We also looked at this, the same water function in terms of looking at technology. Remember, one of the recurring theme that happened this morning is about the labor. Okay, how expensive is the labor, actually? That's because of the, whether you consider labor as one of your own cost or not, free, things of that nature, actually. So when you look at that, depending on the type of technology, whether you're using a pulley and bucket or rope and washer or motor pump or solar pump, actually, how many hours you may have to spend. Let's assume this 400 millimeter is what we agreed to apply as an irrigation. You can see the amount of labor that's required is all the way from 67 hours to only 6 hours. So that's a range we are dealing with, actually, in terms of cost that could offset your potential income or potential profit and so on and so forth, actually. So all this information, the production, the environment information, all those things went into our economic analysis to look at how profitable it is, actually. So we also looked at the technology, whether you use a drip irrigation technology or a flood irrigation technology, how that may offset both water requirement as well as the yield potential. Okay, how much additional water you'll be wasting your water resources, or how much additional labor you would be used in a flood irrigation technology. If you use a drip irrigation technology, you can also gain, it has got a labor saving. We also looked at, under the gap and constraint analysis, about the nutrients. We all talked about today, just water alone is not going to solve our problem. Actually, it needs to have proper nutrient inputs, actually. So again, here we are showing you, based on the various rates of application, actually, the urea versus diammonium phosphate. This is a diammonium phosphate of 3 different levels. And if you look at what is the optimal yield, actually, if you don't put any diammonium phosphate, this is where the yield may stop, actually. Okay. So by applying a little bit of diammonium phosphate between 50 and 100 kilograms, you don't really need 100 kilograms. You can, at the 50 kilograms, you can reach an optimal level, actually. Okay. With the urea being around 240, somewhere between 200 to 240 is all you need on the urea side, actually. So this is the type of analysis that Apex model can help us to answer those individual farmers' questions, actually, because each farmers are unique, each farm field is unique, these characteristics are unique, actually. So the models can take into account of each of the situation in order for us to do the detailed analysis at the farm level. So all this information, that production and environmental information, were passed on to our economic model called FarmSim. And the FarmSim able to look at, over a 5-year period, actually, what are the cost-benefit ratio, for example, taking into all the cost, all the input cost, capital cost, sale and price of the commodity, and so on and so forth. You take into all those information, look at the benefit cost ratio, and also it can able to give you the, what we call internal rate of return. Okay, so you can see even at the baseline that just using a pulley, even though it's a more laborious process and whatnot, it is still profitable. Okay, we're not saying it's not profitable, actually, but then there is always constraint, right? People may not find enough labor to do all those stuff and whatnot, actually. And you can see we are able to come up with a benefit cost of 5 times. That is, anything more than 1 is profitable. We are looking at about almost 5-fold here, actually. And an internal rate of return, we are looking at about 1.6, actually. So it's, again, is very good compared to where we are. I'm looking at just the median here, actually. So there are some even more, or some of them are less, but I'm just looking at a median analysis here. We can also look at this gap and constraint analysis in another way. For example, here is the probability of succeeding, and here is a profit. Obviously, this is an Ethiopian currency, birr. And so here we looked at different alternatives, actually. Okay, under irrigation, Okay, if you don't have enough water, you're applying only 100 millimeter water, or irrigating with 250 millimeter, but using a pulley technology with the groundwater, or using the same pulley technology, but instead of same groundwater, but this time you're using drip irrigation technology. Okay, so we looked at all the different combination of the different technology and different nutrient inputs to come up with this cumulative probability distribution, CDF, here actually. So as you can see, if you take a 50th percentile here, you can look at it, even if you had only the under irrigation, you are still profitable. Okay, you are making somewhere around 10,000 BER actually. Okay, but if you are able to get to something like the drip irrigation with the groundwater with a 250 millimeter or more, you are able to almost 3 times or 4 times of that profitability there actually. So that's the type of information were used when you're doing the scaling up activities actually, and this has been verified and validated with some of the data that Claudia and her group has collected in terms of the field survey. Here is another analysis, again, baseline versus various different alternatives. In this case, it's more on nutrient actually. How much nutrient is optimally that we need actually in terms of urea versus diammonium phosphate, 240 to 100 versus 50 to 120 or 300 to 100. So you can look at the various, again, cumulative probability distribution of, again, if you take a 50th percentile, you're talking about a significant differences between the current baseline versus what you could achieve if you were able to put at least somewhere between, 240 to 100 is the most ideal in this situation, or even 300 to 100 is also another option. So this is one of the slides that when Dr. Lecoq said, okay, we are doing all this complex stuff actually, how am I going to present all this stuff in one slide or one thing actually to take home? So we borrowed it from our sister innovation lab, SIL actually. So they recently come up with some, how I'm going to do all the sustainable indicators of putting them all together in one slide actually. So we attempted this. It still need to go through some more improvements. We need to get some gender impact and other stuff incorporated in here actually, so it's not complete yet actually as of now. But this gives you an idea. In one graph, you will be able to see the various alternatives. Each line represents either baseline or an alternative scenario, and it looks at various indicators, whether it's a production like yield, how stable is the yield, meaning the variability within the, by irrigation using resilience or climate variability, for example. Profitability, okay, how stable is the profitable? Erosion, the environmental impact factors, the nutrition, the food security, the gender, and of course, any conflict, like we talked about the land tenure, for example, actually, how that's going to impact in your, whether you can able to have a continuous land during the wet and dry season and so on and so forth. So, again, this is just a mock-up slide. I mean, we have some preliminary results here, but it is not complete. So this is one of the ways we want to express some of our results so that you'll be able to quickly able to synthesize all the information that coming out of these models actually in a one slide or 2 slides. So from this field level analysis of IDSS actually, we can certainly say even at a pulley technology is still profitable, but we prefer to have more labor savings such as solar pump or motor pump in order to take full advantages of the irrigation potential. Drip irrigation certainly showed us more promising here actually in terms of efficiency as well as the yield potential. The impact of environmental impact is very minimal at this point actually because we are mostly irrigating from the ground. We are not talking about the surface water storage or check dams or any kind of water harvesting structures yet. And of course, the nutrition actually, because of the diversity, I know there was some discussion this morning, we are not anywhere doing a very detailed analysis unless what's done by IMI and IFPRI actually. With our minimal analysis, we are able to show there is enough resources to go around to increase the fat and calcium content intake by the family. So next, I'm shifting gears to, okay, now that we have applied these models to the field based on the data that's collected, based on the verification that was done, and so on and so forth actually, now how do I going to scale it up to a regional and national analysis, actually. So, so one of the fundamental questions is why do we need to do this, actually? So this is basically to make sure our agriculture production, environmental sustainability, as well as household income and nutrition from the household scaling up to at what scale of investment is applicable. Sometimes it's more important not, finding location where not to do investment than where to do the investment, actually. So our analysis can clearly show you where you should not be investing your resources more than where you should be investing your resources. And of course, we want to make sure the environmental and social economic impacts, we need to look at that, and what are some of the strategic investment areas. So with that, let me get on to this upscaling analysis. I know it's a very busy slide. I don't expect you to read all of them. I just wanted to show you the various moving parts here, actually. So all the things that you see on the top, they are all the inputs, okay? And that input went on. These are all either satellite coverages or elevation maps or soils map. All of them are taken from the local data set, actually, local resources. Where it's not available, we go to the global resources, but still again, we further refine that. One example of that is we took the satellite image and then we went to the SPAM database, actually. SPAM is a specially disaggregated crop layer developed by IFPRI, actually. So that was incorporated in the model to run such as SWOT, the soil and water assessment tool that I talked about before. Then we also ran a suitability analysis, actually, where you can say, what is the potential for irrigation suitability? And this potential map becomes a constraint for our rest of the analysis. And of course, the household survey that Claudia and her group worked on from IFPRI, that economic analysis that came from there also fed into this, what we call agent-based model. The agent-based model is, you can call it as a kind of an optimization tool, but it's more of resource allocation tool, actually. It takes all those constraints where you can potentially irrigate and how much water is available for what crop, how much water is required to grow that particular crop, and what is the environmental impact of that, actually. It takes all those information and runs on an agent by agent, meaning each pixel by pixel, to look at what is the optimal resource allocation for that particular agent. So this is one of the new innovation that came out of this lab. This was not done before, actually. Before, the same analysis was in the previous work that was funded, actually. It was done through different set of tools, actually, but ABM is something that was new from IFPRI developed over this project, actually. Okay. So I already mentioned this about the SPAM, the spatially production allocation model. So we use the agricultural data of what crop is grown where by 1 kilometer by 1 kilometer square pixel developed by IFPRI as an input to the SWOT model. And then, of course, we spatially explicitly estimated through SWOT how much water is required to grow the crop, what crop can be grown in a sustainable manner, and at the same time passing all this data into the ABM model, actually, the agent-based model. The agent-based model can provide information such as what is the adoption probability, actually. So if you know what are the input requirement to grow a particular crop, what is the chance that you can grow? If there's no constraint at all, of course, you can grow almost anything, actually. As you have constraints, it will automatically optimize based on economic and environmental sustainability. Okay? So based on that, you'll be able to know what is the adoption probability, what are some of the environmental risks and water scarcity that you need to consider, and what will be the economic benefit, and how many people will be affected or be benefited from this process, actually. Okay? So that's the major outputs from the agent-based model. So with that basic introduction, I'm going to jump into some of the results. So here is the suitability analysis that was done, where we overlaid lots of information one on top of other, actually. And this is the final product out of that, actually, that shows you at what suitability, actually. Obviously, red or yellow or low suitability, green is a higher suitability there, actually. So you can cut it off at any point, actually. You can say, okay, I'm comfortable with given all the uncertainty, I want to be at least 85% sure that I want to be at least selecting something that is suitable 85% of the time or more, actually. So that gives you a rough idea about 12% of all the rain-fed area in Ethiopia, which equal to about 6 million hectares of potential land that could be potentially used for irrigation suitability. Okay? And not only that, actually, we can also break it down by the regional Ethiopian region, actually, where you can do. So you can see already say this Abe, Rift Valley, as well as Gibe, right? Yeah. So these are the three regions that came about to be the top candidates in terms of where the potential could be implemented, or the irrigation area, irrigation suitable areas. So based on the SWOT model analysis, we are able to show you how much is the water availability in terms of surface runoff and how much is the groundwater recharge. In this project, we only consider the groundwater potential, actually, because we did not talk about any of the water harvesting structures at this point. But moving forward, we definitely want to include this water resource that's available, because this is available only during rainy season, but we are going to irrigate during dry season. So unless you capture this somehow, this is not available to you during the dry season. Okay? And here is the amount of onion yield under very wet condition and a dry condition, because the model was run for nearly 30 plus years, actually. So we can able to look at under a different resilience condition, actually, different rainfall pattern condition, what would be the potential, actually. So that when you're looking at your analysis, you can have constraints, very tight constraint, or very liberal constraints, actually, depending on how you want to do the analysis. This is the amount of water required under a under a wet season versus dry season again, actually. Okay. So there is lots of information. I'm just showing you one example of one crop here, actually, but you can start thinking about, we did almost about 15 different crops and all kinds of analysis with this, actually, before that data was passed on to the agent-based model. So the agent-based model was able to take all those constraints, including the land constraint, the suitability constraint, then all the input that went on, like the crop yield, the environmental, the crop the amount of water requirement, and all those stuff. It came up with a map here. Again, it may be difficult for you to read. Again, here, green means highly adaptable. Red means not suitable for irrigation, not going to be adapted. That could be due to environmental concern, production concern, or it could be water availability concern, actually. Okay? So all I'm showing you only the area that is agricultural area. We masked out all other areas so that we don't need to show all this other stuff. So even though the model was simulated for everything, including the fodder and everything, we are just showing you only the agricultural impact or agricultural land area here, actually. Okay? And on the right-hand side, we are showing you where are the water scarcity. If you start continuing to irrigate this over a period of time, so there may be an area that you need to watch out, actually, if you don't have proper recharge. Okay? In other words, you may not have a resilient water availability for a very long time. Okay? So one has to keep that in mind, actually, before the investment goes on, actually, how or what we need to be careful about these areas, actually. Okay? So again, the red means here bad, and yellow means okay. So, but in this case, it's mostly red here, actually. So with this analysis, we are able to show you by region, depending on what cropping system you want to follow, vegetables or pulses, fodder, total number of acres or hectares that could be under irrigation, how much is the profitability, okay? And then finally, the number of people that could be benefited from that, actually. So these are all the output or output from the ABM model. We come up with approximately about $2.6 billion US could be the output here, with about 0.8 million people will be affected because of this, or benefited from this process. I'm just highlighted the three regions, Amara region, SNNP region, and Oromia region, actually. Those are the three highest regions that could be benefited from this small-scale irrigation impact. We are also continuing this research in the other two countries. This is very preliminary results from Ghana and Tanzania. This is the first iteration of the model was run. We are still going through the refinement on this, but we just want to show you that the similar results are available where the suitability and also where the water scarcity could be implicated, actually. And the amount of area is about 210,000 hectares, about $285 million, and about 0.68 million people maybe benefited from this small-scale irrigation. And the next one is for Tanzania. Again, it's a national level analysis actually. It's mostly you can start to see there is a pattern emerging. That's because of the transportation constraints. A lot of areas that you cannot transport what you make out of that. That's one of the layers that go into this analysis actually, and the population centers. So those are the two things that may sometimes constrain where you can unlock your potential. Okay, so we have roughly about 500,000 hectares and about 1.3 billion US dollars, and about 2 million people maybe benefited from this process. Again, it's very preliminary at this point. We are still looking through these numbers. In addition to all this stuff, actually, we are also very recently started asking ourselves, actually, these models are very complex. Am I able to go and train every one of them to make use of this model and whatnot, actually? So we started thinking about developing a dashboard type technology that uses the power of the IDSS on the back end. So this is mainly meant for managers, policymakers, and somebody who's going to be, it's not meant for every researchers to use that. I mean, they could use potentially, but it's more for policymakers and managers and planners and implementers and including the investors and so on. So they could be coming in here and asking the different type of questions, different set of constraints, and thereby all the models are pre-built and pre-run, and those results will become available on the back end for you to simply a screening tool or a visualization tool to find out where exactly you should be considering your investments and what will be the impact of that and so on and so forth, actually. So this is a tool that's work in progress. It's not complete yet, actually. It's still work in progress, but just want to show you where we are heading with this. So the major conclusions on this scale-up activities is we have definitely enough land, enough water available, but they are not everywhere. We have about, in Ethiopia, there's about 0.8 million hectares of land is available with about $2.6 billion of production or the profitability. And SSI, the small-scale irrigation development, can propose some water scarcity. So we have to be careful with that, actually. So I'm shifting gears from the field and regional analysis to capacity development. One of the things that when we embarked this project, actually, one of the things we said, actually, we are not only just going to be doing this project for the sake of doing, but we also want to make sure we can institutionalize it, we can transfer the knowledge, whatever that we gain, to the folks in the respective countries, actually. So when Dr. Clark said, okay, when you're doing this kind of training, we normally need to pay for people to come and attend the stuff, actually. We said, no, we don't want to do that. There need to be some kind of incentive for them, motivation for them to come and attend the training. So we never paid for anybody to come and attend our training in any of these countries, actually. So these are all people voluntarily spend their own time and resources to come and attend this training. Other than our trainers going from here, actually, there was no other cost involved from the trainee side. Actually, they have to pay their own way to come and attend the training. So the training is a continuous process, right? I mean, you can't start and stop anywhere, actually. So it's a continuous process. Nicole put together this wonderful slide, actually, where we talked about the seasonal training, the biannual training, and sometimes repeated more than once the same training just to reinforce that, actually. But then also we do it at the multiple levels, all the way from the farm level, local level, to the national research institutes and so on, so for universities and so on. And of course, we also trained all the IDSS models, including how to conduct surveys, how to do field interventions, and so on and so forth. Then there are some special subjects like Claudia and her team was mentioning here, actually, they did a gender training, for example, for specific groups. So they all get benefited from that process. So there is a lot of special microfinancing, gender training, fees, irrigation fodder, and value chain, and so on and so forth. So at the farm level, IMI has conducted a lot of farm days or training days and demonstration days and so on and so forth, actually. They were able to capture overall about 938 producers, civil servants about 115, private sector about 36 of them, and civil society is about 193. So overall, we had about 907 male and about 375 female. That's a pretty good ratio for USAID target, actually. So we are not that lucky when you do the IDSS, actually, but field level, IMI did an excellent job of capturing all the irrigation technology transferred. And the training is not all the same, actually. So it's varied across, actually. So it always from the water and soil management, because remember, these people have never worked with the irrigation before they introduced this stuff in there, actually, especially for the dry season irrigation. So there needs to be a lot of things need to be taught, especially how do you do the irrigation scheduling, the post-forest handling, and conservation agriculture, credit training, and so on and so forth, actually. So there are lots of various degree of training, both in terms of the duration and who is the targeted audience and how frequently it was done and where it was done, like in all countries in most of the situation. Okay. The field training is also helped the local universities to employ students to go and collect data, to engage in them, actually. So the project kind of paid for them to collect data and then use the data for the research and get their master's and PhD and so on and so forth. So there were quite a few of that, actually. There is about 26 graduate students were supported through this, and about 10 undergraduate students were involved in this project, actually. So again, it produced about 22 thesis papers, 1 awarded outstanding, and 3 international conferences, and 14 students completed thesis by this year, actually. Okay, that's a great achievement within a short span of time, because anytime you are relying on field data to conduct your thesis, you are at the mercy of Mother Nature, actually, sometimes. So this really helped to have a significant output from the field studies that they're able to carry out to do the research. The capacity building on the gender, again, more than 150 national experts were trained on that, actually, how to use gender in irrigation context. And a lot of resources were not only available during the workshop time, but also they made it available as a blog and papers that's available through their website. Thereby, it reaches out to beyond just the 150 participants who may be at that meeting, actually. And then there were other, in Tanzania, there is also an organization have adapted the work that came out of Claudia's group, but also in Ethiopia, the ATA has now looking at gender and the sensitivity to irrigation and so on and so forth, actually. So it's not only the studies were conducted for this study, for this project, but that somehow translated to the national agencies for them to start adapting that in their own respective framework. So come to the capacity building of the IDSS, actually. So here we had brought in graduate students, a master's student and a PhD student to the US. North Carolina A&T hosted a PhD student, and Texas A&M hosted a master's student. And the master's student is graduated as of this month, and the PhD students are about to be graduated by end of this project year, actually. So we'll have 2 graduated from here. But in addition to that, we also have extended period, like a 3 months training of bringing in the students who are working on the ILSSI project in the respective countries getting the degree, but we brought them here for specialized training here, actually. Okay. So we had so far about 9 of them, actually, that's going through this kind of training. And then we conducted a regular workshop, a 5-day workshop in the respective countries. We have conducted 10 of them so far, actually. And then we also, at the request of some of these institutions like ATA and others in the respective countries, we have tried to go back and train them individually, the government staffs and the government organizations, in the use of our tools, actually. And thereby we are able to institutionalize the IDSS in the respective organizations. Okay, and of course, we continue to work with other stakeholders and CG centers. So the IDSS training is varied. It's all the way from a beginners to a more advanced, like what we call IDSS clinic. And then we had a special training for ATA that's just concluded about 2 weeks ago with a very favorable response from them, actually. In terms of institutionalizing all these IDSS, universities are the first one to adapt. Then, of course, the government institutions followed that, actually. And then now we are also working with other NGOs in that region to adapt the same, actually. Especially most of them are from Ethiopia, but we also have other countries coming forward with that, actually. So overall, we had about 10 trainings, Out of the 10 trainings, we had about a total of 668 people get trained on that, of which total males were about 555 and the female was 113. So we didn't get the same thing what IMI was able to achieve from the field training. But it shows you the number of individuals from each country, how many of them participated in these trainings. And I did a very quick anecdotal exercises after just about a few minutes ago, actually. Before the ILSSI project came about in 2013, the number of peer-reviewed papers published in Ethiopia was only about 27 about the IDSS tools in general. And since then, there was 38 additional new papers are published only in the last 5 years, actually. I'm talking about the last 20 years versus this last 5 years. So we already exceeded almost about 100% of them, actually. And if you go back and look at each of the authorship, we can able to go back and track them through one of our training and other contributions that came through this work. So I know it's a long list. I don't want to go through every one of them, actually. I just want to hit the highlight. The overall, we have produced more than 50 different reports. It's available on our ILSSI website. We not only produce those reports, every one of the data that is used in this model is available through the Dataverse, actually. That's part of the public data sharing that USAID recommended us, actually. So all this model inputs and outputs and all the products that generated out of this stuff is all available for anyone to use at this point, actually. Okay, everything is published at this point, and including the groundwater, the potential for suitability of irrigation, and so on. Not only that, we also developed new tools like the ABM model I was talking about, actually, the GIS interfaces for the SWOT model and things like that. So all of them are public domain. Everything what we do is public domain, and it is available through our system. So IDS has really helped identify the strategies and to mitigate the gaps and constraints. The small-scale irrigation under optimal fertilizer increases agricultural production and economic outcome. Solar pump is the most viable and economically feasible workable solution. Major limitation was the labor, which we all discussed extensively already. So the environmental impact is very minimal so far. The sustainability for the potential of small-scale investment or small-scale impact is about 4.5 million people with about $2.6 billion is what we come out of that analysis, actually. Okay? And the rest is, I'll stop right there. I think I talked too much. Thank you.